We had a good understanding about how to perform the various operations on the binary search tree, namely searching, insertion, and deletion. And we concluded that the running time for each one of them should not be simply just big O of log n or big O of n. Rather, the more precise way to say that would be big O of h. H being the height of the tree. And what can be the minimum and maximum for the height of the tree? We learned before, for any binary tree, the minimum height would be log n. And the maximum height will be n. And what we really want to do in this week is to see, is it possible to really always maintain the heights of the binary search tree, which is a binary tree, to be always around log n. That's something we would like to see. In that way, we will be able to reach very efficient searching operation, which is the fundamental basis for the insertion and deletion. That's something we'll talk about this week. So the title of the slide really suggests the new bits about the balance. What does it really mean to be for a binary search tree to be balanced? That's something we'll focus on in the first part of this week. Let's now go over some learning outcomes for this week, and then we'll move on to talking about balance property, and then see how we can maintain a balance. So we will hope you to understand, number one, about when the worst case running time of a binary search tree search occurs. And that's really mainly like a brush up from what we had earlier. We wouldn't really go into the algorithmic details like how you can perform a search, but we wanted to review quickly about what can really happen in the worst case. And we're going to talk about the high balance property. So we want to know exactly what kind of property we want to maintain for the tree in order to achieve the efficient searching running time, which is big O of log n. And also we want to see how we can perform the so-called rotations to restore the tree balance. So this will be the main learning outcome for sure at the end. So this will be the solution. We want to first of all to see what kind of property we really want to achieve for the binary search tree. And then the solution will be to perform rotations whenever possible. Let's now brush up about why we would need a balanced binary search tree. Let's see why it will be the case. So after insertions into a binary search tree, the worst case running time, well, always the accurate running time will be big O of h, but the worst case for the h will be linear. So that's why it will be the maximum for the heights, which will be big O of n over here. So this sentence here, it really summarizes what we learned before. But let's see some examples. We will go over 3 different ways for achieving a tree with the maximum heights, linear height more precisely. So we got example number 1 with decreasing keys. We got example number 2 with increasing keys, and example number 3 with in-between keys. And let me emphasize, these are just 3 example ways for achieving the maximum heights. There might be many other ways for achieving the same results, the worst case. But definitely, you want to just get a feeling about how the worst case can be achieved. Let's take a look. For example number 1, we will start with the empty binary search tree, and we want to insert the keys in this particular order. And let me emphasize, these values over here are key values. For example, 100 over here is the key value. However, in every node in the binary search tree, you should really store an entry, including the elements and the key. But to really talk about a shape, how we can form a particular shape of the binary search tree, only the search keys matter. So that's why I'm only showing to you the key values over here. But I should really understand that implicitly, we also got the element value for the tree node as well, for the entry. Let's take a look. The first key to insert will be 100. And given that we start with an empty binary search tree, this node or this key will just become the root automatically. So we got 100 over here. So the first one is pretty trivial. That's the first one. And the second one will be 75. For every node you want to insert, you have to follow the steps that we laid out last week about how you can insert into a binary search tree. I'm going to assume that you actually know how to do that. Very briefly, start with the root, and we know that it should be strictly less than that. So that will be the external node that will be returned, for which you have to convert into an internal node that stores the key value 75. I'll leave you to review the detailed steps that we said earlier. Right, so this one here will be 75. So 75 over here will become the left child of 100. The next one will be 68. If you follow through the search process, it's going to become the left child again for 75 over here. Next one 60, which will become the left child for 68. And next one 50, which will become the left child of 60. And next one, final one will be 1. which is going to become the left child of 50. So that's about the insertion. Obviously, the height of the tree cannot be log n. That's simply not the case. It is the worst case indeed. How many nodes have we got? We actually got 1, 2, 3, 4, 5, 6 inserted. What's the height? Height will be defined as the maximum depth of the child nodes. And for this tree, with the root being over here, what will be the child with the maximum depth? It should be the leaf node at the bottom over here. What's the depth? 1, 2, 3, 4, and 5. So that will be the height for the tree rooted at this node over here. All right, let's now make some annotation over here. So you can see from here down to the leaf node over here, the height is actually exactly equal to n minus 1, right? The number of nodes minus 1, which is big O of n. So that's our main conclusion up to now over here. By inserting the keys in this particular order, we resulted in a tree over here. It's still a binary search tree. You can definitely do the in order traversal. You still get a sorted sequence of keys. However, the height over here is really big O of n, meaning that if you want to do anything related to searching, it's going to be linear. So that's unavoidable. Let's now take a look at the second example over here. The second example would be we want to insert in this particular order over here. Let's do that quickly. So we start with 1. So 1 is actually going to be over here. And then 50 is larger than that. So we're going to make it as a right child over here. So that's going to be 50. And then 60 over here, also the right child. And then 68. It seems like we are doing the opposite order, right? Which is okay. I just want to show you different example of resulting in a linear a tree with a linear height. And then 75, which will be over here, and then 100. Okay, so these are the ones. And you can see again, what will be the height for the tree rooted at this particular node? The child with the maximum height, the maximum depth, should be the child at the bottom over here. So the depth should be 1, 2, 3, 4, 5. So we got something similar as before. It just slanted the opposite way. Okay, over here. So this one over here, the height will still be n minus 1, which is big O of n. So we are resulting in equally bad tree over here in terms of its linear heights. And as an exercise, I would like you to try to draw the tree over here, right? I'll put down as an exercise for you. What would be the tree, how would the tree look like after inserting this particular sequence of keys? And you can try to convince yourself that the height will still be linear, which means it's really just equally bad as the previous ones, which we drew together. Right? And it's very important for you now to really conclude to yourself, it is actually possible for the tree height to be linear, meaning that the searching operation is not necessarily just log n always. It can just very common to actually reach to the linear running time for the searching, unless you do some very explicit cautionary steps whenever the tree might just go out of balance. I'll put in quote balance because we haven't really defined the formal notion of balance just yet. We will do that in a moment. Okay. All right, let's now go. Let me just say once more, just a very important conclusion over here. For both of these over here, for this one over here, and also this one over here. So this means the searching has the worst case. Running time would be linear. That's why we're doing this exercise in the beginning together. Big O of n. Okay. Let's now go back to the slides, and then so these are the two examples I just drew to you, to show to you. It's called a so-called one-pass tree, which we spoke about earlier when we spoke about the bounds for the binary tree. Okay. One is left slanted, the other one is right slanted. You can see very obviously from the visual diagram. And this will be your exercise to draw. So to really avoid the worst case running time, like an zero balance tree, we're going to define what the balance property really is in a moment. And we need to take actions as soon as the tree becomes unbalanced, meaning that whenever you want to insert or delete some node into the tree or from the tree, you want to make sure if the insertion or deletion results in an ill-balanced binary search tree, you want to restore the balance right away. That's something we'll talk about in the next part.